All right, let me get to where we left off. Blah, 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 blah. What's that say at the top? Not hear anything, turn up volume. Well, is my volume? My volume's maxed out. What is this? Okay. Actually, let's do a warm-up one, a non-trig warm-up one, just to make sure we got it. And we'll pick up from there when Matt gets back. Give him 1 minute. The other Calc class is supposed to be coming in right now. Trying to stay motivated here. Come on, Matt. All right, we're getting started. Okay, we'll start off with Nick. Go.
Don't use all of the numbers except for plus and negative.
Well done. Abby?
Intercept, y-intercept would just be not wait 1 -4.
Negative 1/4. X-intercept. Sure.
Multiplied by x squared minus.
Okay.
Yeah, 1.
Yeah, I think that one through again.
Oh, no x-intercept.
No x-intercept. We get this silly thing would say 0 is equal to 1, and that's not true. So no x-intercept, and the y-intercept you said was negative 1/4. Yes, this is the one we did. All right, Nick.
Symmetry would be
What do we do?
set x equal to negative.
Okay.
And that's same. So
it has y axis symmetry. That's even function. Okay. Abby?
So negative vertical, -2 positive.
Yeah, we get that from the domain.
Console divide by x squared.
Take the limit, so we're dividing by x squared, and we're going to get 0 over 1, which is 0, and negative infinity.
Just 0.
Yep, 0 over 1. Yep, so 0. So on the left side and the right side, the function goes to 0. Okay, Nick?
Increasing,
which means we need to
take first derivative.
Look at you. You went 2 days ago from not knowing a single answer to knowing all the procedures. All right, first derivative, go. Well, what are you going to use?
The quotient.
Quotient rule. Low d high minus high d low over low squared. Low.
X squared minus 4.
Derivative of high?
0.
0, so that goes away. Minus high d low.
This 1
times
2x
all over
the bottom square.
There we go. So that turns into 0. That turns into minus 2x. Therefore,
it's just
click. Can you do anything else?
No.
No. Now we take that in,
set
it equal to 0 and solve.
The bottom.
And so you're left with x is equal to 0. I skipped the step where it says negative 2x equals 0 divided by negative 2. Okay. How do we figure out whether it's increasing or decreasing? We take the any restrictions along with the critical number 0, and we determine whether it's positive or negative. But we plug it not into the original function. We plug the intermediate values into the first derivative. So -3, -1, 1, and 3. We plug those all in. I'll do the math for you real quick. And we get those points right there. Where it's negative, it's increasing or decreasing, or it's positive, it's increasing. Okay. Abby? In order to do with min and max, we need to find
First square.
which we already found right here. So we already solved and we got 0. And now we take that fact that the min and the max happens at 0, along with our statement about increasing, decreasing, we use some common sense. So at 0, it's to the left, it's left, it's increasing. 0, -2 to 0, it's increasing. So to the left of 0, it's increasing, and to the right, it's, which makes it a increasing, increasing, decreasing. Ish, you can't see this, but I'm drawing increasing, increasing, decreasing, decreasing with my laser pointer. Increasing, 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 decreasing, decreasing, decreasing.
Okay, then 0 is a max.
Then 0 is a max. Okay. Nick,
Function point. So
inflection points, we need to,
take second.
take the second derivative. So that's going to be
Quotient.
quotient and chain rule. Quotient and chain rule. Low D high minus high D low over low squared.
X squared. Y squared.
Okay. Derivative of the high minus high.
-2x.
And then we need to do the chain rule of this one. So that would be 2 times x squared minus 4 times the derivative of the inside, which would be another 2x. Okay. I didn't write these in order, but that's what it would be. If I wrote them in order, then the minus 2x would be here and this would be over there. Okay. All right, what did you say you wanted to do on this one now?
No, it's like cancel
A cancel. How many we're going to cancel?
the x2 minus 4.
How many of them though?
Just
one off of every term. So the first term now just turns into 1. The second term goes away. Third term turns into a 3. Okay. Now all we're going to do right here is to the distributive property, do some multiplication. 8x squared minus 2x is 6x squared. So 6x squared plus 8. There's your. Now, a lot of people look at this and say, hey, factor out a 2. You could, if you wanted to. Okay. So there's our second derivative. What do we do with that? Set it equal to 0 and solve. This is the problem that we ran into the previous one. I should probably show the step, but I'm not. Well, you multiply by the denominator, it turns into 6x squared plus 8 is equal to 0. Keep going.
Well, but 8.
So you get 6x squared is equal to -8.
Divide by 6.
And then
It's square root.
you're just taking the square root of a negative number, which you can't do. Therefore, it has no inflection points. None. Now, it leads you to believe that if it has no inflection points, it's strictly concave up or concave down. But we can see it goes increasing, decreasing a couple different times. Therefore, it must. And so what's happening is that where the inflection point should be, there ends up being a vertical asymptote. And that's why we don't get an answer for inflection points, because the vertical asymptotes are taking up those spaces. We still need to figure out, though, for concavity, no inflection points, but for concavity, right, where it's greater than or less than 0, greater than 0 or less than 0, we still take the second derivative and see where it's greater than or less than, or we look at those values right here. So I'm going to take my vertical asymptotes with my critical point 0 and just plug in numbers to see whether I get positive or negative. We plug in numbers when we get positive and negative numbers. I didn't do this, but we could do this, right? We find out that concave up, remember, will give you a positive number, right? It's concave up, so you get between -2 and 0, you get a plus. To the left of -2, you get a plus, and then you get minuses, minuses. Did I do that backwards? Did I do it right? Negative infinity to -2 is concave up, so positive. From 2 to infinity, so that's a plus. And then concave down, -2 to 0. And then concave 0 to 2 is concave down. So I did do that right. Okay, so that's what we get. All right. So that's how we teased out that information of concave up and concave down. Now, the only thing left to do is to graph this sucker. This is kind of where the bell rang, right? So let's see. We start off with our intercepts. The only thing we have is a y-intercept at -1/4. We have our vertical asymptotes at plus or -2. We get our horizontal asymptote, which is the x-axis. And then we simply look at our increasing and decreasing and our concave up, concave down. Says it's concave up between negative infinity and -2. So I mean, it's got to go in an upward direction, but it hugs the x-axis right here. So therefore it's got to look like this. And then on the right side of -2 vertical asymptote, it says it's right side between -2. It's concave down, which means it must increase and make the half of that U shape. And then we can, because it has y-axis symmetry, we can reflect it over it or continue, your choice. We know it looks like that, and then it looks like that. Make sense? The actual graph of it kind of looks like it's more flattened right here, right? We did not test any points over there. We just said it had to go through that y intercept. If you had tested the points out there, you'd see it's more flat. Make sense? Okay. So anything left? What's left that we didn't do? Oblique asymptotes, right? So Abby just said she skipped it, right? But do you remember finding oblique asymptotes from pre-calc? Well, what did you do to find them? Okay, well then you don't remember. You remember what they look like. They look like this, right? Okay, so how do we find them? So this year, remember, we'll define them as a limit. We did this before. So what's the limit as you go to negative infinity here? What's the limit as you go to positive infinity? Okay, so if it ever goes to positive or negative infinity, that's how we're going to define them, right? So let's think about this, right? So I have a function here, the blue one, y equals f of x right here. And then I have an oblique asymptote right here, the red, okay? What happens as we get closer to positive infinity? Between the red and the blue. What happens as we get closer to positive infinity? Squeezes, it gets closer and closer and closer. So what's happening to the distance between red and blue? Getting smaller and smaller. So if I know that an oblique asymptote is a straight line, y equals mx plus b, I know a function is just plain old f of x, and we said as we approach positive infinity, that distance, what I just drew, then we could write this as that distance as f of x is going to be a y value. Mx plus b is going to be a y value because it's literally defined as y equals mx plus b. So that if I subtracted these two, this value would be the distance. And what do we know as we go to positive infinity? It gets smaller and smaller. In other words, it's approaching zero. So that's how we're going to define this, right? So what's an oblique or a slant or a diagonal asymptote? It's a diagonal line, y equals mxb, that approaches f of x as x goes to positive or negative infinity. Kind of makes sense. That was basically, in word form, the description of what I just showed you. Now, what I included in there, it says as that limit, that distance, right? That f of x minus mx plus b, that distance is going to be going closer and closer and closer to the value of 0. So as the limit, as that distance approaches 0, that would define what the oblique asymptote is. Or I should say, it doesn't define what the oblique asymptote is. It would define what's happening at infinity. Okay? So for all oblique asymptotes, right? That thing right there, as x goes to infinity, the value is going towards 0. Does that make sense? Right? F of x would be the y value of the function. Mx plus b would be the, let's see, that would be the y value of the oblique asymptote. And if we subtract the two, as x approaches positive infinity, that value should be going towards 0. This is why we didn't give you this last year, because you didn't know what a limit was. And now you do. The obvious question, though, is, great, that's what defines the asymptote. The obvious question is, how do you find it? And that is, once again, goes back to the pre-calc question, right? When do they occur? How do you find them? All right, you ready to be reminded what you did in pre-calc? What did you do? Right? Given a function, right? That's a polynomial that's rational, where the numerator is a polynomial and the denominator is a polynomial. Oblique asymptote occurs when, You remember this, right? When the top number is one more than the bottom number. The only time this occurs is when the top power is one more than the bottom one. So they're very easy to identify. You simply find the highest power of the numerator, you look at the denominator, and if that top power is one more than the bottom, then there's going to be an oblique asymptote. That's how we defined it last year. Where's all your comrades at? Are they in trouble? Okay. Okay, great. That identifies there is one. It was the second part of the statement that was the pain. You remember what the pain was? Okay, so the top highest power is one more than the bottom. So there's an oblique asymptote. Do you remember what you did? You did long division. Long division. Well, thank you for that, right? Hey, it was a weird long division. A year ago you did this. In fact, they're doing it right now, break out. And the issue is that you do the long division until you either it divides evenly or you get a remainder. If it divides evenly, or if you get a remainder, the dividend is the answer minus the remainder. We just don't include the remainder. So it's either going to divide evenly or there's going to be a remainder regardless which case we're in. We ignore the remainder 0 or the remainder of something. The quotient is the answer. You're going to need an example of that? Going to need an example of that? Yeah, let's do an example of that. Do we have an oblique asymptote? Yes or no? How do you know? Okay, for some reason on my slide, I don't actually, oh no, we're going to graph this. We're going to sketch this curve, right? We're going to do this whole thing. And then when we get to asymptotes, we're going to do the long division for the one. Okay, we start off with Nick. Let's start off with Matt. Go, domain. What did you say? And solve. Okay. Is it ever possible to get a 0 in the denominator? If you take x and you square it, that will always be. And if you add 1, you can't ever get to 0, so therefore, all real numbers. All done. You almost figured that out all by yourself, and you were just stuck on the what happens if there isn't one. Okay, Nick.
Intercepts.
Okay. I always do the x-intercept first.
Set the x is equal to 0.
Set the y equals 0. Thank you. It's only because my way of my slides. You don't have to find the x-intercept first, but set the y is equal to 0 and solve. Go. If you're pausing, it's because you don't know what to do.
Yeah.
Just if you have a fraction and it's equal to 0, always.
It's just
No. If you have a fraction, yes, that's the answer, but I'm saying I still want you to make the statement. If you have a fraction and it's set equal to 0, you always move what? You always clear the fraction. And the magic here is because it equals 0, what actually happens, Abby said the other day, and I said, no, don't say that. But then I said, yes, say that. Say it, Abby. Just ignore the bottom. It's just the top.
Yeah.
Right? I wanted her to say, we clear the fraction, we multiply both sides by the denominator. So therefore, you can do that. Now solve that. It's just 0, and that's why I agreed with you at the end there. Okay, so the x-intercept is 0. How do we find the y-intercept?
X is.
Okay, now let x is equal to 0, and we get 0, right? Right, you're okay because you didn't get 0 in the bottom, you got 1 in the bottom, right? If it had just been x squared, then we would have had a problem. Okay, cool. Abby, symmetry, go.
Okay, well, the 2 turns into just x, and the negative x
Negative on the top.
cubed.
Does this look like that? So it doesn't have y-axis symmetry. What if we factored out a -1?
Well, that would make it negative x squared minus 1.
Yeah, but let's think this through. When we factor out a -1, what we're really doing is we're factoring out one -1. We're not multiplying by top and bottom by -1. We're just factoring out one -1.
Oh, then yeah.
Then yeah. So if we factor out a -1, in other words, pull this negative to the front, make that a -1, then that looks exactly like that. Therefore, this has origin symmetry. Okay, it's an odd function, it has origin symmetry. Cool. Okay, not periodic, so we're on to the next one. Matt?
Yes.
Oh, you get the fun stuff. Okay. So now we get the full picture. Now we always have to consider whether or not it has all the asymptotes or just some of them. Does it have a vertical asymptote?
No.
No. Does it have a horizontal asymptote? Well, we got to figure out. Let's figure it out. So it definitely doesn't have a vertical asymptote, right? That doesn't have an answer. Does it have a horizontal asymptote? How do you figure that out? Take the limit as it approaches infinity and negative infinity. Okay, what's the technique? Yeah, and guess what you'd be left with on the top? And then when you plug in infinity, it becomes really big, so therefore infinity, right? So you get an infinity over 1, which is infinity. How about with negative infinity? Not exactly. Now we're throwing in negative infinity. So negative infinity, there we go. And it's not because it's negative infinity that you automatically get negative infinity. It's because of just this particular one. We got an x left on the top. That's going to go to negative infinity. On the bottom, that's just going to go to 1. Yeah? Okay. But you got the bonus plan because you also now need to do the oblique ones. And how do you know we need to apply the oblique one? Because the top power is 1 more than the bottom. I mean, that's pretty quickly forgotten as well, too. All right, so let's do the oblique, which means we're supposed to do long division. Okay. I apologize. I don't have this in the slides. I'm doing this all by hand. I'm dividing the top, x cubed, by x squared plus 1. So what do you want me to write? We're literally doing long division. So what do you want me to write?
X cubed.
And if you remember when we do long division, not only do we write x cubed, we write every single power down to the constant. Okay? We don't do that with the divisor, but we do that with the dividend. So if you have an x cubed, but there's no x squared, you got to write. I want every power. There you go. Plus 0x squared plus 0x plus 0. You have to do that for the long division. Okay? And what are we dividing by? What? What are we dividing by? X squared plus 1. Okay? Remember how to do this?
No.
You just look at the first thing, which is what times x squared is x cubed? So we put an x, and then we do the multiplication. X times 1. Where should I put it? No.
At 0.
At 0x. So I put x. X times x squared. And then it's long division, then it's long division. So what do you do next? I draw a line and so which means it changes all these signs. So this now becomes I'm not asking for the answer. I'm asking what to do with the x cubed and the x. So now we have to change their signs. Don't say make them negative, because if they were negative, they would make them positive. So we change all the signs. Now we add. So we do, in fact, get. But then we get 0x squared. And negative x, and then plus 0. Okay? What times x squared is 0x squared? 0. Okay. Nobody would do this, but if we did this, right? I'm not gonna put a plus 0. Okay, so 0 times that would be 0x squared. 0 times 1 would be 0, and then we would subtract. That sounds
You forgot
ridiculous.
the x squared.
Yeah, but 0 times 1, because we're putting 0.
Yeah, but 0 times x squared is 0x squared.
Oh, got you. I got you. Yeah, I did do that. Okay. So nobody would put that 0. So the question is, that would go away, and we'd be left with this, right? Does x squared go into negative x? And the answer is, so that's your remainder. And what did I say? I said you can ignore the remainder. You just look at and that, the quotient is your oblique asymptote. You just add a y. So what's the oblique asymptote? You just add a y. Y equals x. Okay? So the oblique asymptote is y is equal to x. Okay, we will do a practice one for homework as well too. All right. We're on Nick now. What are you doing? Increasing, decreasing. How do we find it?
First derivative.
First derivative. And you got a quotient rule again.
So x squared plus 1
Times
3x squared
minus
x3 2
all over
the bottom square.
the bottom squared. All right, what are you doing? Anything to cancel? Not this time.
I mean, x squared plus 1.
Yeah, well, there's one on this term, there's one on the bottom, but there isn't one on this one, so we
Oh, so
can't
you can't.
cancel.
There's no
So what can you do?
simplify.
Okay, go.
Or distribute.
Well, that's simplifying,
Okay.
right? Yeah.
The 3x squared distributed to the x squared plus 1. 4x squared.
What?
4x to the 4.
What? What are you trying to do?
Distribute 3.
Okay, so what are you trying to do? Speak. What are you trying to do?
Simplify.
No. I'm just asking. You said distributed property. We agreed, and then I asked. You said a nonsensical answer. So I said, "What are you trying to do?"
Put 3x squared into x squared.
Not putting it into. That's division.
Distribute.
We're multiplying. What are we multiplying?
X squared plus x squared plus 1.
So do that.
4x.
Where are you getting a 4 from?
Oh, they're just 3x. 3x 4.
3x to the 4.
Okay. And then just 3x.
3x.
Squared.
There we go. And then I'll do this one for you.
Okay.
All right, now what? Now what?
The 3x fourth and minus 2x.
So you'd be left with,
Just x fourth.
okay? Could you factor out an x squared? You could, right? We know eventually we're going to be taking the double derivative. So if you factor something out, then you just made you factor out an x, then you just made it into a. Could we factor out an x squared right here?
You just made a change.
I just made a. Close. No. You made not a chain. You made a product rule. So if I wrote this as x squared times x squared plus 3, right? Perfectly true, perfectly factored. But now you turned when I do my quotient rule right here, I have a quotient and I got a product rule, which, I'm not going to factor that out. I'm going to leave it like that, right? If you do what I just showed you right here, you will make your life more challenging to take the second derivative. Okay. All right. Well, all we did was found the derivative. Now what? Equal to 0 and solve. And he said the answer is going to be 0 Speak. Think it through. If he sets the top equal to 0, how many things are being multiplied together? 2. So we got the x squared. Clearly that's a 0. What does this one turn into?
Negative.
Think it through. What do you do after you set that equal to 0 and you move the 3? Okay, keep talking.
Negative 3 over 0.
No. So we had x squared plus 3 equals 0. Solve that.
We'd have to take the square.
Continue your thought.
So square root of 3.
No, look at it again. You were so close.
Square root of a negative number, which means there's.
Which is why it doesn't exist. Okay. So the only answer we got was 0. The only critical number we got is 0. What do we do with that?
Put it down below.
Okay, and then we pick numbers
Left
and right of 0. Okay, you're picking,
negative 1 and 1.
and we would just look at the domain to make sure that's okay. Is that okay? So negative 1 and 1, and we throw these values into
The first.
Okay, you can either throw it into this one or this one. It doesn't matter which one you want. Okay, so if I
That's positive.
that's positive,
Positive.
that's positive,
Positive.
positive. So that's going to give me a positive. Okay, what about 1?
Positive. Positive.
And if everything's being squared or to an even power, everything's always going to be positive. All right, so where is it increasing or decreasing?
From negative to negative, or
It never stops increasing. It's just increasing everywhere. It's increasing everywhere, but remember, at 0, that was our critical point. It's that's where the slope is equal to 0. Okay, does that make sense? Okay. All right, Abby, you're up. Mins and maxes. Well, clearly,
Well, it's increasing, no decreases, so there is no multiple.
okay. Well, we're supposed to take that, set that equal to 0, solve. We got 0. But how do we find its minimax? We look at this, and since it's only increasing, then therefore it does have none. Okay. Matt?
what's next? Okay.
It's right there.
Oh,
How do we find it?
okay.
Second derivative. Now, I wrote this, but it sure would be easier if we wrote it like the original one, which would be y prime is equal to x to the 4th plus 3x squared, because then it's just a polynomial that it will be easier to take the derivatives of. Otherwise, you got to use all right, go. What's the quotient will say? Low D high, high D low. Low is no, low is just low.
Oh yeah.
Times derivative of high. Now you open parentheses. Okay. Minus low D high minus high. Derivative of low. Okay. All over. Don't get that. Okay. Oh dear Lord, look at that. How long that is. All right, what are we gonna do? I got an x squared minus 4. I got this whole thing. Nope, I don't have an x squared, so I can't cancel. Nothing to cancel. So the only thing I can do is no, we're not solving anything. Simplify it, right? So a whole bunch of multiplication and distributive property. Well, this one's easy. But in order to do it to this one right here, right? Oh, wait a minute. Never mind. There is an x squared minus 4. No, that's a plus 1. Never mind. I was right the first time. Okay. So we're going to do whatever math we can. So this is this one here, right? Okay. This one's still being left alone because it's being multiplied. And then over here, we can multiply 4x times this, which would give us that, right? Times that. Okay. Now what? Now what? Now what? No. Oh, then we'd still have to solve this. Let's do all the simplifying we can do. Is there anything else we can do? Yeah, distribute even more. Okay, so what did I do on this step right here? I did 2x cubed plus 2x cubed, which is 4x cubed. I factored out 4x from this one. I factor out an x squared from that one. Okay. Well, I can move this x squared over here. That would make it x cubed, right? Anything else we can do? What happened here? I did one extra thing. Now notice on this step, I have an x squared plus 1 on the top. I got an x squared plus 1 on the second term. I got an x squared plus 1 on the bottom. So I could cancel 2 of them. No, 1 of them. Sorry, 1 of them. So 1 from that term, 1 from this term, 1 from that term. Could we now do some multiplication? Yeah, that's what we're going to do. Ignore the red marks here. I'm going to do some canceling here in a second. Okay. So I'm going to multiply this binomial times this binomial and distribute this minus 4x to the inside. I did that. And notice we get 2 terms that go away. So we got a 4x cubed and a 6x cubed, which gives us, hey, look, minus 12x cubed. This thing really turns into much smaller things. I'm still left with that 6x. Okay. Wouldn't you agree that this would be easier to deal with than the other mess we had? Okay. Now, go ahead.
Equals 0.
Equals 0. So what do you want me to write equals 0? Just the top. Notice I factor out a minus 2x. Okay. So just the top. I'm not sure why I wrote that a second time right there. Oh, I know why. Go. Okay, so we would get, okay, so you would get, well, what would they be? Zero and root 3. There you go. Well done. So that one, and then if I divide by the other side, right, I get the other one. All right. If you notice, it says the word inflection points. I haven't shown you this before, but I'm actually calculating the y values right here. So plus or minus root 3, right, and 0, right? But I'm also taking that plus root 3, throwing it back into the original one and figuring out I get it. I've done some rounding here, by the way. It's not literally negative 1.3. It's negative. It's a roughly negative 1.3. That way we can graph these things. Okay. Cool. All right. So concavity, we take that whole darn thing and we find out where it's positive or negative. Okay. Let's see if we can figure this out. These were by issue or where we had the problems with was root 3 and 0, plus or minus root 3 and 0. So we pick points in between, toss them in this, and see if we get positive or negative. You okay if I just show you the answer? Okay. All right. So there's your concave up and concave down. Now we got to take that big whole hot mess and graph it. Okay. So let's see. Take that big whole hot mess. Let's see. We got intercepts at the origin. We have no vertical asymptotes. We do have an oblique asymptote. What do you want me to draw? Diagonal line. Yep, there we go. That's a pretty good estimate of what y is equal to x would be. And then what other things do we have? We have our inflection points, right? So there's an inflection point. There's your other inflection point, roughly. This, I'm just going to claim that's negative root 3, and that's negative 1.3, and that's positive root 3, and that's positive 1.3. And then we're going to follow our concave up, concave down. What is it? What is it? It's concave up between negative infinity to negative root 3, which is this point right here. So we go concave up and then concave down. There's your concave up. This curve didn't turn out exactly the way I wanted it to, right? It should be more like that. That gives you more impression of concave up. This gives you more impression of concave down. So it goes concave up, then negative 3, then it goes concave down, then it goes concave up. And once again, you can kind of see that it curves around a bit like that. There's your concave down with your last one. There you go. And there's the actual curve. Yay, we did it. All right. Here's what you need to do. You need to look over homework and pick the one that had the oblique asymptote. We'll do that one together.
Where?
The rest of this issue, I'm going to do this by hand. All I'm going to do is going to go over the long divisions. So they got that. And I got your email. And yes, you know, the plan that you had, we'll do that plan when you show back up.